All right. Every discussion of periodic motion and simple harmonic motion has to lead with the mass spring system because it's the most familiar and also the most easy to analyze. So, with spring constant K, there's a mass m attached, and it's stretched a distance of a, the amplitude from equilibrium. So first, we're just going to show that this system does exhibit simple harmonic motion. So at the point given, we have a couple forces. So we have the weight of the block, mg. Then we have an equal balancing normal force because it's not accelerating vertically. There's nothing weird happening with the surface or anything. But then the actual interesting part is the spring. So the spring is displaced to the right, meaning that there is a spring exerting a force trying to send it back to its equilibrium position, force of the spring. So we get that the net force on the block spring system is just going to be negative of the spring force, negative because it's to the left. And what is spring force? Well, the spring force is just going to be negative k times x, where x is the distance from equilibrium. So we have that F is equal to negative kx, which implies that we have simple harmonic motion, because F is proportional to the negative of the displacement. Now we want to derive an expression for the angular frequency of the motion, which is omega. So to learn about things like frequency and period for simple harmonic motion, what we want to do is we want to set up the F equals ma equation. So we know that F is equal to minus kx. But also, we know that F is equal to ma. So ma is equal to minus kx. But also, we know that the relationship between a and x, we have m times the second derivative with respect to time is equal to negative k times x. Or rearranging, we get d squared x dt squared is equal to negative k over m times x. And by definition of simple harmonic motion, the number in front of the x is always going to change depending on your system, but this number right here is always omega squared, because that's our form of the differential equation. Is the second time derivative is equal to negative angular frequency squared times x. So this just means that omega squared is equal to k over m, which means that omega is equal to the square root of k over m. And you'll see this a lot where the angular frequency of a motion is typically equal to some sort of restoring force constant divided by some sort of inertia. So the inertia of this block is its mass, and the restoring force is characterized by the spring constant. This is also a formula that is worth committing to memory for a mass spring. It comes up a lot. Derive an expression for the period of the motion. So we're actually done with the analysis of it with forces, things in that realm. We just need to figure out how to convert angular frequency to period. So angular frequency is how quickly you're going around a circle, how many radians per second. So omega is defined as 2 pi f. So the frequency of the motion, meaning how many revs per second you're doing, is omega divided by 2 pi. But also, since frequency is equal to the reciprocal of the period, because if you're doing 2 cycles per second, your period is a half second. We have this nice reciprocal relationship. Well, that just means 1 over t is equal to omega over 2 pi. Or we get t is equal to 2 pi divided by omega, which is equal to 2 pi times square root of m over k. Because when dividing by omega, that just means flip the fraction over. So this is the period of the mass spring oscillator. So we have two expressions. If you want the number of seconds it takes to repeat, you need t. And if you want the angular frequency, which is the thing that goes inside the argument of the cosine, that's omega. And these are formulas that are either on your equation sheet or just worth memorizing. A block of mass 2 kilograms is attached to a spring and is allowed to undergo simple harmonic motion on a frictionless surface. The equation of the block's position as a function of time is modeled by a sine differential equation, or a sine position function, where position is measured in meters and time is measured in seconds. All right. So, notice you're given a sine or cosine function as position. So that means that this is going to be simple harmonic. So we're given that x is equal to a cosine of omega t plus phi. And now we're just going to match the terms. So a is equal to 3. Omega is 8. And phi is 0. So this means that we started timing as soon as we released the block at its maximum point. So what's the amplitude? Well, the amplitude is 3 meters. Is the motion simple harmonic? Yes. It's because x is equal to some cosine function. So it just follows our parent function formula for being simple harmonic motion. Solve for the spring constant. Well, all we're given is the function. So we have to figure out what about this function tells us the spring constant. And it is definitely not the amplitude, because the amplitude has nothing to do with the period of oscillation. So it must be related to this 8 inside, which is our angular frequency. And the only formula we've had so far with a spring constant in it is the frequency or period equation. So omega is defined as k over m under a square root for the mass spring oscillator. And we were given both omega and m. So we're given the block has mass 2 kilograms. And the angular frequency is the number inside the cosine, which is 8. So we're just solving 8 equals square root of k divided by 2. So squaring both sides, we get 64 is equal to k divided by 2. So k is equal to 128 newtons per meter. Solve for the maximum velocity of the block. So there are some shortcut formulas we could take advantage of here, but we're just going to go in and derive it from scratch. So this time at least. So we know that x is equal to 3 times cosine of 8t. And we actually don't need to know simple harmonic motion for this. This is just a calculus question. Maximum velocity. Well, velocity is equal to the derivative of x with respect to time. And after doing a derivative here, we get negative 3 sine of 8t, but we can't forget the chain rule factor of 8. So we get that v is equal to negative 24 sine of 8t. And just using our knowledge of sine, we know that sine and cosine are bounded, so they can't be greater in absolute value than 1. So that means that our V max is simply going to be 24 meters per second. It's the amplitude of the velocity function if we want to think about it that way. But also, if you're just feeling like doing a formula out of this, we can use the following result, which we basically just proved, that V max is equal to the amplitude times omega. The amplitude of the motion was 3, and omega was 8. So we get 24 meters per second once again, as we expected. Solve for the max acceleration of the block. So we can imagine what's going to happen here. So if we had x was equal to 3 times cosine of 8t, v was equal to negative 3 times 8 times sine of 8t, and then a is just another derivative, which I don't need to flip the sign this time, but I do have to chain rule again. So I get that a is going to be equal to, so we're going to see the acceleration function is equal to negative 192 cosine of 8t, which means that the a max is a very large 192 meters per second squared. Or you could derive a similar expression to that for V max, and you can show that A max is also just going to be given by the amplitude times omega squared. One of the best parts of simple harmonic motion is the fact that it connects to energy. So if we are assuming no friction, which we often are, we're allowed to use any of these lovely equations for the total energy of a mass spring oscillator. So at any point, the energy is just the kinetic and potential added together, which in equation form, it's the velocity at any point and the extension at any point plugged into their respective formulas. But it's probably easier for us to look at the extremes where all your energy is kinetic or all your energy is potential. And even if the problem is vertical, we actually don't need any MGH at all. The proof of that is a bit beyond what we really need to do with this, but just realize it's all based on the fact that we can choose the 0 point of potential energy wherever we want. And if we choose it in a clever enough way, we can get all the GPE changes to vanish. So it really doesn't matter. So suppose a particle of mass m is attached to a spring of force constant k, and it's undergoing simple harmonic motion. It's released from rest at time equals 0 at its amplitude. And we're given the oscillation period as t. And we want to derive the max velocity as our first part. Well, for any energy problem, we can always use the fact that for the spring, K plus U at the first point is going to be equal to K plus U at the final point. And the easiest one here is to use the fact that it's released from rest at a distance of A. So that means that at the first point, the total energy of the spring system is 1/2 Ka squared. That was one of our expressions for total energy. And then at the end, we want V max. So it achieves maximum velocity when it has no potential. So we're just seeing the full spring potential getting converted into the full kinetic. So we're just solving 1/2 Ka squared equals 1/2 mv max squared. So you do get a cancellation. We get the 1/2s cancel, and we get that the V max is just going to be equal to the square root of Ka squared divided by m, which is equal to square root K over m times A, which, funnily enough, is that omega times A number we used before. But we actually aren't allowed to use omega, so. All right, solve for the kinetic energy of the particle when the displacement of the mass is A over 2. So with all these mass spring energy problems, we definitely want to use the fact that kinetic plus potential is a conserved quantity. And we're asked to do all this stuff in terms of K, A, and possibly M. So what we should do is we should use the fact that at the start there's 0 kinetic energy and there's 1/2 Ka squared worth of potential energy, which is also the total energy of our system, is equal to the kinetic energy at the end plus 1/2 times little k times the extension is only A over 2 there. So we get 1/2 Ka squared is equal to final kinetic energy plus 1/8 Ka squared, because we have to square the 2 in the denominator to get a 4 when those combine. So then we can come over here and we get kinetic energy final is just going to be 1/2 Ka squared minus 1/8 Ka squared, which is equal to 4/8 minus 1/8, which is 3/8 Ka squared. So that's our actual answer, is 3/8 Ka squared. But also, you can factor out a 1/2. And see that this is actually 3/4 of your total energy. So when the mass is at A over 2, it only has a quarter of its original potential energy. So that must mean the other 3/4 are kinetic. Now we want to solve for the spring extension in terms of K and A. Solve for the extension when the particle speed is 3/4 of its max value. So we'll do this a bit of a different way than we did the one up here, just to show kind of how dealing with energy and using conservation makes this a bit easier. So at this point, the kinetic energy is equal to 1/2 times m times 3/4 of V max squared. And that's equal to 1/2 times m times 9/16 times Vmax squared, which is the same thing as 9/16 times the quantity, 1/2 times m times Vmax squared. And the reason I did it this way is because 1/2 mv max squared is also our total energy. So the kinetic energy at this point is 9/16 of the total energy. And this helps us convert from the V, which we have to get rid of. We can't have V in our final answer. So we actually have to do this in terms of A. So if the K plus U has to be equal to the energy total, well, we can see that this means that U has to be equal to 7/16 of the total. Because we had 9/16 that were kinetic, so the other 7/16 had to be potential. So we can solve this out now, because we know that energy total is 1/2 Ka squared. So 1/2 Kx squared at that point has to be equal to 7/16 of the 1/2 Kx, or sorry, Ka squared. Because again, that's our total energy, and the 1/2 Kx squared is how much we have now. So 1/2 cancels, 1/2 cancels, K. And then also, we're just going to get X is equal to the square root of 7/16 times A squared, which is just equal to the square root of 7 divided by 16 times A. And that's our answer. If you did this just by doing K plus U equals K plus U, you would get an equivalent answer, but it would be quite a bit nastier to deal with algebraically. And then lastly, find the ratio of potential energy to kinetic energy at 1/8 of a cycle in. So what we want is to figure out the ratio of U to K at that point, which is equal to 1/2 Kx squared divided by 1/2 mv squared, which is just going to be equal to Kx squared divided by mv squared. So we have to figure out what x and v are at this specific time. So what we could do for this is we could actually just look at the whole functions and plug in and see what all that is. Or we could actually think about it for a second at this specific time and see what simplifications happen. So we know that we're releasing it from rest at time equals 0. So x is going to be equal to a cosine of omega t, which means that v is going to be negative a omega times sine of omega t. So why this is helpful is if we just think about what 1/8 of a cycle looks like for each of these things. Well, just to make things simpler, this will work for all values, but we'll just pretend if omega was equal to 1, that would mean t over 8 is equal to 2 pi over 8, which is equal to pi over 4. So we're just asking, what is happening to sine and cosine, the standard graph, when it's at pi over 4? And well, so we know that x of t over 8 is just going to be a times cosine of pi over 4, which is root 2 over 2. And v at t over 8 is going to be negative a omega times root 2 over 2, because sine and cosine have the same value at that point. Because again, also what we're asking is, what is the height and what is the length and height of a point along the circle at t over 8, which is this point right here, and it's that 45, 45, 90 triangle. So they're going to have the same value. Inside, we just pick up that extra factor of omega. So let's do it now. So we got k times x, which we said is going to be a times root 2 over 2 squared divided by m times negative a omega times root 2 over 2 quantity squared. And now we do get some nice things to cancel. So we've at least removed a lot of the variables we don't want. So we see that the a cancels, the root 2 over 2 cancels, as does the negative sign. So all we're left with is k divided by m times omega squared. But we can't have omega in our answer, so we have to substitute away. So omega squared was equal to k over m by definition. So that means that our ratio is just going to be k over m times the reciprocal of omega squared, which is k over m, which is equal to 1. So actually, an eighth of a cycle in is a special point where you have just as much kinetic and potential energy for your mass spring oscillator. That's a very hard question. This part D is very tricky. And I only asked it because I knew we'd get this special cancellation an eighth of a cycle in. Okay, and lastly for energy, and talking about graphs, we have a block hangs from rest, and then you're pulling it at its max amplitude and then releasing it and watching it cycle. So we're going to graph like everything here. All right, so first, the position graph is probably the easiest to make. So we're starting at its max amplitude. So at the 0 point, it reaches its max amplitude because we're starting it from that point. Quarter of a cycle later, we pass through 0. A quarter of a cycle later, we reach max negative displacement. Then we reach the 0 point again of 0 displacement, and then we complete the cycle. So this is just plotting a. So this is just going to be plotting a cosine curve here. So we get our cosine curve. Oh, I was close to getting it on the first try. And something like that. Okay, so, and again, we're saying this is like x equals a cosine of omega t. All right, now we'll just do some derivative curve sketching. So, you could look at this a couple ways. I might just choose to look at this as the velocity is going to be equal to the derivative with respect to time of the position. So let's do it that way, where instead we're basically asking what is the slope of the blue graph? Well, at the top, the slope is 0. So the slope is 0 at every. So the slope, we're just going to mark the 0 points first. The slope is 0 at the start, and then every half period. Because again, points of horizontal tangents are where the slope is 0. So we know that's our graph. And then we see it reaches maximum negative slope a quarter cycle in. So that's where the slope is highest in the negative direction. So we get that. And then we see the sign pattern just repeat like this. And for the amplitudes of this graph, we know that the max and min are actually just going to be the amplitude multiplied by the chain rule factor of omega. Or if we just explicitly took the derivative of the function we graphed, we would get a negative sine function. And let's do it again. So acceleration is going to be the derivative of the velocity function, or it's just going to be negative omega squared times the position function. So that might be the easier one to do because we have harmonic motion. So we can just flip the graph upside down that we graphed in the first part. So we're just graphing a reflected cosine curve for this. Or you could use the slope argument for the taking the derivative of the purple curve. All right. So we're just gonna zoom by this a bit quickly here. So again, I just reflected my original graph. To get that. So you can see it is just a reflected version. And the max and mins of these graphs, well, you get two chain rule factors because we took two derivatives. All right, momentum. Kind of a strange thing to graph for this, but well, momentum is just going to be equal to mv. So it's actually just the velocity graph scaled by a factor of v. So this is going to be m a omega, and this is going to be negative m a omega. So it's literally just the velocity graph just scaled a bit. So oh, missed it here. There we go. That was not good. My graphing by hand with the cursor could use some work, but I think we get the idea. So notice this is just the velocity graph just scaled. All right, now for some interesting ones. The force graph. So the force is going to be equal to negative some constant times the displacement. So it's going to be a negative reflected version. So a negative meaning a reflected version of the original graph for position. So this is just going to be KA, and this is going to be minus KA. And we can reason why this should make sense. So if you pull it all the way, well, you're going to experience maximum force, but in the opposite direction. And if you're at the equilibrium position, you experience no force. And if you're all the way at negative displacement, you're experiencing maximum force the opposite way, and so on. So we get this curve. All right, now for kinetic potential and total energy. All right, so for kinetic energy, we know that K is equal to 1/2 times mv squared. And due to the square, we actually can't go negative. So the top value on this graph is just going to be 1/2 times m times omega times a. Because omega a is the V max, and we're squaring that. All right, so we're just gonna square this purple graph. So it's easy to just spot the 0 points. So if you're not moving, you don't have kinetic energy. So where the velocity is 0, the kinetic energy also has to be 0. And then also, when your V is maximized, so is your kinetic energy. So notice we're actually getting double the maxima here because the positive and negative V both correspond to maximum kinetic energy. So instead, we get a cosine or sine squared graph here. And then a couple ways of thinking about this one, but for the U graph, well, this is very similar. U is equal to 1/2 times K times X squared. So that means our maximum value for this one is going to be 1/2 KA squared. So we're just going to square the X graph. So when the X is pulled all the way out, well, that means its potential energy is maximized. And then when it reaches 0, it has no spring potential. And then it just keeps bouncing back and forth between maximum and minimum potential energy, like so. And notice that the K and U graphs exactly overlap in where their maxes and mins are relative to one another. So notice that at this point here, the minimum of the U graph is the max of the K graph. But even though they're trading with each other, the energy total remains constant. So the total energy is just going to remain some constant value, which is equal to 1/2 Ka squared, or 1/2 times m times omega A squared. Because notice that if I add these two curves together, the purple and blue, I'm always going to hit this line. And that's that. Lots of stuff going on with the spring system. I really enjoy this representation question because it really makes us think about all the different quantities.